Swayam Prabha. Digital India. Educated India.
Welcome everyone. This is the lecture 4 of module 7. In the previous lecture, we learnt about the various processes of attenuation. Preferably, we learnt about the three processes that are the geometrical spreading, multipathing, and the scattering. In today's lecture, we will focus upon intrinsic attenuation, and then we will derive the formula for the intrinsic attenuation with the help of quality factor, and then we will be having the summary of today's lecture. The intrinsic attenuation, which is also known as anelasticity, is the process when seismic wave energy is converted to heat when the seismic wave produces irrecoverable deformation. So it happens mainly at very high temperature. Suppose the temperature is more than 900 degrees C, and in the mantle, and where the deformation takes place, and this deformation cannot be reversed, and the energy is lost as heat. So to look at this process, let's examine a case of a spring with a mass. So you can see there is this spring here which is attached to a mass here. And in this particular example, you can see that the spring is attached to this mass m, and the constant associated with string is k, that is your spring constant. And if we write the equation of the motion for this particular simple harmonic motion, then it can be something like this: m d square ut by dt square plus k ut is equal to 0, where u is the displacement with respect to time, and this is displacement is for the mass m, and k is the spring constant. If we would like to find the solution for this differential equation, that it can be written something like this: ut is equal to a e to the power iota omega naught t plus b e to the power iota omega naught t, where a and b are the constants, and the mass is moving back and forth with a natural frequency omega naught, that is equal to under root of k by m. One example of the general solution to this differential equation in the form of displacement can be like this: ut is equal to a naught cos omega naught t. And if you look at this particular expression of SHM, or the simple harmonic motion, this oscillation will continue to happen forever. But in the real life, the oscillations are damped and the energy will be lost in the form of the heat. For the energy to loss in the form of attenuation, then we are going to introduce a term, that is the damping term or a dashpot, so that the energy will decay, and the damping force due to the dashpot will be proportional to the velocity of the mass and will oppose the motion of the simple harmonic conditions, so that the amplitude of the motion will decay. In that case, the expression may be something like this: m d square u by dt square, then plus gamma m du by dt. So this is the damping term here, plus the ku is equal to 0, where gamma is the damping factor. And if we want to simplify this, then we can equate q, that is the quality factor, is equal to natural frequency by the damping factor. And then we can rewrite this equation, and in the rewritten form, if we divide the equation by the mass on both the sides, then it will become something like this, and where the gamma has been replaced from this particular equation, gamma is equal to omega naught by q, then du by dt plus omega naught square u t is equal to 0, and k is basically replaced by the natural frequency using this particular formula here. Now, this differential equation we can solve using the displacement, where the displacement will be having the complex exponential, and this will be ut is equal to a naught e to the power iota pt. If we incorporate this into the equation 1, then it will become something like this. And if we want it to satisfy all the value of the time, then this particular term here should become 0. So this is becoming 0 here. And if we consider p to be complex, then we can break it into its real and the imaginary parts. So let's suppose p is equal to a plus iota b, and if we square it, then it will become something like this. And when we incorporate this into this particular equation here, then it may give equation something like this. So if we just separate the real and the imaginary part of this particular expression, then we will have to equate the real and the imaginary part individually to 0, so that we can have the solution of this particular equation. So real part is a minus a square plus b square minus b omega naught by q plus omega naught square, that will be equal to 0. And the imaginary part will be minus 2 iota ab plus iota a omega naught by q, that will also be equal to 0. When we solve both these equations, then what we will get, the value of the b, that will be equal to omega naught by 2q, and the value of a will be equal to omega naught square minus omega naught square by 4q square, that will be equal to omega naught square in bracket 1 minus 1 by 4q square. And if you look at this particular expression here, if q is less than 1 by 2, then this entire thing or the value of the a will become imaginary. So in real earth situation, what actually happens, the value of the q is generally very large, on the order of hundreds. So we should not be worried about this imaginary thing into this particular expression for a. Thus we can define omega, that will be equal to a. We are defining omega, that is equal to a, that is equal to omega naught, that is the residual frequency, in bracket 1 minus 1 by 4q square to the power 1 by 2. And we can rewrite ut, that was this particular expression here, where ut is equal to a naught e to the power iota pt, where p is a plus iota b. And when we insert the value of a and b into this expression for ut, then it will become something like this. And when we will separate the real part of this solution for the damped harmonic displacement, then it will become something like this. So if we will draw this displacement onto a graph, then it may look something like this, which will be decaying as the exponential term. That means the exponential term is expressing the decay of the signal's amplitude, or you can say the overall amplitude, and this will be superimposed onto the harmonic oscillation, that is basically defined by this particular cosine term. So you can see the energy is decaying something like this exponentially, which is superimposed over to the cosine term, that is the cosine term. Amplitude is keep on decaying with time, and the q value, that is the quality factor, is inversely proportional to the damping factor, that is gamma. So the smaller the damping, the greater the q is. So as the damping increases, the quality factor decreases. That means the decay in the amplitude will be faster. And there is a concept of the relaxation time, which is basically the time that the seismic wave takes to decay to 1 by e of its initial amplitude a naught. And if we will solve this, then the time for the relaxation, that is t 1 by e in subscript, that will be equal to 2q by omega naught. So if we calculate the energy in an oscillation system, then we will find that it is proportional to the square of the amplitude. That means energy as a function of time is equal to half k at square. That k is the constant term, spring constant, and that will be equal to 1 by 2 k a naught square e to the power minus omega naught t by q, and this can be replaced by E naught, and that will become something like this. So if you will look at this term and also this term, then when you will compare, then what you will see, the energy decays faster than the amplitude because of the negative exponent in this particular equation, which is uh, twice large as equation 5 or equation 4. So this is basically as large as twice than this particular expression here. So if we want to have some points to remember, that means the attenuation for the seismic wave and a variety of other physical phenomena are often discussed in the form of Q or inverse Q. Although Q has some convenient values, but Q inverse can be having the additional advantage that it is directly rather than inversely proportional to the damping. When we speak of the Q of the surface waves, body waves, and the crustal phases like algae, and the variations within the earth for the quality factor of P wave and the quality factor of S wave, which controls the attenuation of P and S waves. The anelastic structure of the earth given by variations in Q alpha and Q beta. So these are the quality factor for S and P wave, which is analogous to the elastic velocity structure because Q can be viewed mathematically as imaginary part of the velocity. So we can derive, or we have derived, the decaying oscillation that was given by this particular expression of the displacement where P is equal to A plus iota B, and we also saw that A is equal to omega and B is equal to omega star. This omega star is basically nothing but omega naught by 2q, and since we are considering that A is equal to omega and omega naught is equal to omega, for being the attenuation is very small, that means Q is very large. In case of Q is very large, then we can regard omega naught as equal to omega. Hence, we can write quality factor inverse is equal to 2b by A, that is 2 omega star by omega. And when we treat the attenuation as an imaginary part of the frequency and dividing it by the wave number, then we can get the expression for the corresponding velocity for a propagating wave in the form of the complex. So that will be C plus iota C star, that is equal to omega by k. C is equal to omega by k. So C star will naturally be omega star by k. So C omega by k plus iota omega star by k, that is equal to omega by k plus iota omega q inverse by 2k. So when we see and calculate the value of the q inverse here, then that will be basically 2c star by c. So you can compare this thing with this thing. So what you will get, q inverse is equal to 2c star by c. Thus we can express the attenuation of P and S wave by using quality factor q alpha, q beta to give imaginary part to the velocities. So if suppose the attenuation is 0, that means the quality factor is infinity. At that particular situation, the frequency and the velocity will have no imaginary parts. So we are going to pose the complex part of the velocities in the term of the properties of the material causing attenuation by treating the elastic moduli as having imaginary parts. So for shear wave velocity, we can write the velocity having real part and also the imaginary part, that is the beta star, and we can write this as equal to, if we take the beta common from this particular expression, then it will become basically the beta in bracket 1 plus iota beta star by beta, and this beta star by beta can be found out from this particular expression, since we know Q inverse is equal to 2 omega star by omega, and that we have seen in my previous slide, that is 2 omega star by omega. And this can be written as, after dividing both the denominator and the numerator by the wave number, then what we will get 2 beta star by beta. And when we incorporate this value into this particular equation, then it will become something like this. So that is beta 1 plus iota q beta inverse by 2. And since we know that beta can be written as under root of mu by rho, so it can be written something like this: mu plus iota beta star by rho to the power under root, that is equal to beta 1 plus iota mu star by mu, that is to the power under root. And if we apply the Taylor's expansion into this particular expression, then it will become something like this. So when we compare this thing with this particular shear wave velocity beta plus iota beta star, that means when we compare beta plus iota beta star, that will be equal to beta 1 plus iota mu star by 2 mu, then what you will get the value of the Q inverse. That means this expression you are comparing it with, that is basically equal to beta 1 plus iota Q beta inverse by 2. So that will basically, this thing and this thing together will give the Q beta inverse, that will be equal to mu star by mu. Similarly, the quality factor for P wave can also be calculated. Then it will become Q alpha inverse, that will be equal to K star plus 4 by 3 mu star divided by K plus 4 by 3 mu. So the attenuation term of the imaginary part of the compressibility and the rigidity can also be written, that is Qk inverse is equal to K star by K, and for the rigidity Q mu inverse is equal to mu star by mu, that is basically equal to Q beta inverse, because Q beta inverse is also mu star by mu here. So these quality factors are related to those for the velocities by using this formula, where L is equal to 4 by 3 beta by alpha square. So in general, the little energy is lost in compression. So Qk inverse will be very small, because the energy in the compression will be the very small for the attenuation, and thus most of the attenuation for P waves occur in shear. That makes Q alpha inverse, that will be approximately equal to 4 by 9 Q beta inverse. Techniques for measuring Q in the earth follow from those used to measure Q for the decay of the oscillation, and then we can take the natural logarithm of the envelope, that was this particular equation. If we take the natural logarithm of this particular equation, if we consider ut as the amplitude at, then it will become something like this. And when we make the graph of it, then the Q value can be found from the slope of the logarithmic decay. Alternatively, if we have the successive peaks coming in one full time period, that is 2 pi by omega naught, that is the time when the two successive peaks are apart from each other, and those will be having the amplitudes as follows: a1 t1, that means the amplitude of the first peak at time t1 will be equal to a naught exponential minus omega naught t1 by 2q, and after the one full time period, that means a2 t1 plus capital T, that is the time period, one full time period, that was equal to 2 pi by omega naught, and that is equal to a naught exponential minus omega naught t1 plus t by 2q. And when we take their ratios a1 by a2, then it will become exponential in bracket minus omega naught t1 by 2q minus omega naught t1 plus t by 2q is equal to exponential pi by omega. So Q can be found from this expression that will become pi by ln A1 by A2, and if we want to have another way to view Q is as the number of cycles the oscillation takes to decay to a certain level. The number of cycles n can be found out by taking the ratio of the time by the period, that will be omega t by 2 pi, and that will further approximately equal to omega naught t by 2 pi. That assumes that the attenuation is small enough, that means q is greater than 1, so that omega is equal to omega naught. The amplitude at time tn after n cycles will be written something like this. That is a tn after n number of cycles is equal to a naught e to the power minus n pi by q, and this will have this kind of graph that we have seen already. So in case if we have at, the envelope of the oscillation can be written something like this, and if we take ln of the both sides, then we can possibly find the value of the q by taking the slope of the natural log of the amplitude envelope as it changes with time. And if you have successive peaks one period apart, then you can definitely say a1 t1 is equal to a naught exponential minus omega naught t1 by 2q, and a2 t2 a naught exponential minus omega naught t1 plus t by 2q, and when we take the ratio it will be something like this. Since t is equal to 2 pi by omega naught, so a1 by a2 will become exponential minus pi by q, and atn will be equal to something like this. That we have seen already in this particular example. This is just the elaboration of what we have seen previously. So this tells us how the amplitude of the wave varies with time at a given location. Another way to look at thing is how the amplitude varies in space, since t is equal to x by c. So when we replace this t by x by c, then we can possibly write amplitude as a function of x, that is a naught e to the power minus omega naught x by 2 cq, and c is the velocity, q is the quality factor. And for the ray theoretical method, the integrated effect of the attenuation along the wavelength can be written by this expression. So in the frequency space, we can write the expression something like this. So this basically represents the decay in the amplitude or the variation in the amplitude with frequency. A omega is equal to a naught omega e to the power minus omega t star by 2. And this will basically allow to get at variations in the attenuation in the earth, and for a given earthquake observed at multiple seismometers, the relative variation in T star can be gotten at by ratioing the natural log of the spectrum of the event at each seismometer. The natural log of A omega is something given by this expression ln A omega is equal to minus omega t star by 2 plus ln A naught omega. So the ratio of A1 and A2 with respect to frequency can be written something like this, and this is basically because of the same source, that's why their values are same. So ln A0 A1 omega by A2 omega is equal to minus omega by 2 T1 star plus omega by 2 T2 star, and that can be written something like this: half delta T star, that is the difference between T1 and T2, and that will be multiplied to omega. So variation on these techniques are regularly used in seismology. So we use this in the various forms for the techniques to basically quantify the ratio of A1 and A2, and that is basically regularly used in the seismology. So now if we talk about the quality factor and whatever we have learnt and can be written in some of the points, so we can define n as equal to q. So atn is equal to a naught e to the power minus pi, that is 0.04 a naught. Thus after q cycles the amplitude drops to a level of e to the power minus pi, or 4% of the original amplitude, and more than 95% of the amplitude is lost after approximately q is equal to 8 number of cycles, that we can easily calculate by taking the ratio of a1 and a2. Q can describe the oscillation decay in either space or time, And for the standing waves like normal mode oscillations, Q describes the decay of the amplitude with time. And for traveling wave, we replace T with X by C. That will basically represent the amplitude variations with the position X or the distance. And that can be written something like this. A as a function of distance will be equal to A naught e to the power minus omega naught X by 2C Q. And here this particular graph shows the frequency dependence of the seismic waves in the mantle using SCS waves. If you remember, SCS waves are like, if suppose this is your core and there you have your mantle and there you have a earthquake, and then the earthquake energy is traveling as S wave and then get reflected from the core mantle boundary, then it will have a small c with it, and then after the reflection it is traveling as capital S wave, then it will be recorded at the surface, then the wave's name will be SCS. Since it is entirely traveling in the mantle, so it is a very good, I can say, good phase for the understanding of the properties of the mantle. So this is preferred for the or you can say it is a very good measure to understand the average mental physical parameters. So frequency dependence of the seismic waves in the mantle using SCS wave. So this basically shows the quality factor of SCS with respect to the frequency to understand the frequency dependence of the mantle attenuation. So Q varies with frequency and it is basically constant at very low frequencies of about maybe 0.0001 to basically zero point 0.1, and then it basically increases with frequency like this. So Q values, if you consider for the normal modes, are basically lower than those for the higher frequencies wave, such as the long period body waves and the short period body waves. And this is the summary of today's lecture. What we have learned today is, for the damped harmonic oscillator, the displacement can be given as ut is equal to a naught e to the power iota omega t plus iota bt, that is equal to a naught e to the power minus bt e to the power iota omega t, with a is equal to omega, that is equal to omega naught 1 minus 1 by 4q square to the power under root, that is equal to b is equal to omega naught by 2q. And the relaxation time is when the amplitude decays to 1 by e of its initial value. So that relaxation time is t in subscript 1 by e is equal to 2q by omega naught, where q is the quality factor and q is inversely proportional to the damping factor gamma. So the smaller the damping, the greater the q is. The energy decay is given as Et, that is half KAT square, and if we expand this A, that is A naught e to the power minus omega t by 2q, then it for the A square term that will be like this, and this particular term that will further be equal to E naught e to the power minus omega t by q. And if you look at this equation, compare it with the amplitude equation, then energy decays twice as faster as the decay in the amplitude. Quality factor can be formulated as Q inverse is equal to 2B by A is equal to 2 mega star by omega, and Q inverse is equal to 2C star by C, that is in the form of velocity. And for the P and S waves, the quality factors inverse for the S waves is equal to mu star, that is the shear modulus, divided by mu, and Q alpha inverse is equal to K star plus 4 by 3 mu star is divided by K plus 4 by 3 mu. And the Q can also be find out the values of the amplitude recorded at 2 consecutive cycles, that means A1 and A2, so that will be equal to pi by ln A1 by A2. So these are the references. So we are going to meet in the next lecture, that is the last lecture of module 7. And thank you so much. Bye bye.